have this object T mu. Usually we call it as energy momentum tensor or stress energy momentum tensor. Momentum tensor. Okay. So it gives you the energy, it gives you the momentum, it gives you stress as well. Okay, because you are stressed. Okay, so I'll show you all these things. So we have this very objective, this very equation, T mu that's equal to C. So this we have shown yesterday. So it implies you are having this objective T mu ds mu that is it. Okay. So this very objective we have shown yesterday, it's a conserved quantity. Okay. We call this object as, what is this object called? Let's see. So this very object is conserved. Okay, let's write on this thing. Only this much is conserved. Okay, now let's look how many equations are there. Let's try to understand this equation deeply. So it's a sort of continuity equation. We have seen in the this very object last time. This very equation gave equal to 0. This gave us the continuity equation. Okay, this represents the continuity equation. So what was that? Partial rho by partial t plus del dot j, that's equal to 0. Okay, so continuity equation is actually the it gives us the conservation law. Okay, it gives us the conservation of the charge. Okay, here the conservation of charge, this is the charge, although it's now this charge actually is a vector. We call this as a Noether current. Usually the charge here, rho, you call it as a Q here. The total charge in the system, we call it as a Noether charge. So there is actually a theorem. Okay, let me put it this way. Since we are constructing Lagrangians based on the symmetry principles, so there is actually a relation between symmetry and a conservation law. Okay, a symmetry provides a conservation law. Let's think this way. So let's have you rotate some object along z-axis. About z-axis you rotate some object and say it's invariant under rotation about z-axis. Okay, let's move this very pen this way, and you say this very I mean my system is invariant under rotation along z-axis. Okay, so it remains the same if you rotate it along z-axis. What happens then? There is a conservation law. What kind of conservation law? Z component of the angular momentum is conserved, is it? So you are having a symmetry. Symmetry means it is symmetric about, let's say, z-axis. Then this symmetry provides you the conservation law. Okay, it's a continuous symmetry in the sense. Continuous in a sense you can continuously move, okay, along, let's say, through an angle theta. You change it continuously, okay, through 0 to 2 pi. Clear? समझ आओ? In other words, if you are having a symmetry, it means a continuous symmetry means conservation law, and a conservation law implies what? Symmetry. Based on these principles, we actually arrived at all these Lagrangians what we have done till now. Clear? If you look at the Lagrangian of a free particle, okay, I mean simple free particle, what we assume? Space is isotropic, is it? Sorry, space is homogeneous. And actually that is the translational invariance that gives the conservation of the momentum. Clear? We assumed actually the space is isotropic, the rotational invariance. Clear? And based on these principles, we arrived actually the Lagrangian of the form of half of m q dot square. Clear? You remember this very point? And similarly others. We assume, let's say, Lorentz invariance, okay? We assume gauge invariance. These are all kinds of symmetry in a given system, and we have derived based on those symmetry principles. We wrote these Lagrangians. Clear? Now, when you are when I am saying there is a conservation law based on a certain symmetry, so conservation law implies this very objective. Is this a conservation law? Okay, a quantity which is conserved, okay, under a given symmetry, we call that as a Noether charge, and or Noether current. Okay, so you are having this as a scalar quantity. Rho is a scalar quantity, is it? So this we call as a Noether charge, because this very concept, the relation between symmetry and a conservation law, was given by Noether. So Emmy Noether was a lady physicist, rather mathematical mathematician as well as a physicist. She proved this kind of relation. There is a relation between what? A symmetry and a conservation law. Okay. So if you are having a conserved quantity here, so conserved quantity here is actually Q. Okay. We call that as a Noether charge. Okay. Here it is actually a vector quantity. Yesterday we have seen. So it is this very objective. P mu is equal to 1 by C integral T mu 0 d3 of x. So we call this as a Noether current. Okay, it is actually the energy momentum vector. 4 energy momentum, or rather 4 momentum vector, that is actually the Noether current. Clear? So this is a conserved quantity. Okay. Now let's look at this very objective. So it should yield me the conservation, the continuity equation. Okay. So let's write. So let's take nu is equal to 0 in this very equation. How many equations are there? 4 equations. Okay. Let's try to interpret the quantities. These quantities, T mu nu quantities. Let's try to interpret these. What exactly they give us? Although we have seen yesterday, we have this as a 4 momentum vector. Let's try to interpret it exactly what is going on. Okay. Let's take nu equal to 0 component. Then I am having this very equation. P mu 0 is equal to 0. Okay. So what it gives me? Anybody? So let's write. It is partial 0 T 0 0 plus partial I T I 0 is equal to 0, and there is a sum over I. Okay? There is a sum over I. So what this object is? So it is simply 1 by C partial T 0 0 by partial T. Okay? Anybody? I will keep it as such because it is simply the divergence with respect to I, this very component, first component, it's equal to 0. Okay, do you see it's actually this kind of equation? This, is it? It's a kind of continuity equation. Okay, so that means how many equations I will get? 4 equations. Okay, so now let's integrate this over volume. V, that means we are where x0 is equal to constant hyperplane. So it means, so I am having 1 by C partial by partial T integration T0 0 D3 okay dV. So it's the integration of the volume. That's equal to minus integration of the volume partial I Ti0 dV. Okay. Okay, so can you tell me what this gives me? Yesterday we have seen T00 gives you the energy density. So it will give you the total energy, okay? So let's write. So let me write this way. So let's multiply this C on dV. Okay, it's minus C. Now if you see this is actually the divergence with respect to this index, is it? Is this a divergence? Forget about this 0. Is this a divergence?
Yes, sir.
Everybody? So when I am having a divergence and there is an integration over volume, I can use Gauss Law, is it? So I can convert this to the surface integral. So let's call this as surface S. Okay, then I will be having this Ti0. Let's write some dSi. Okay? Applying Gauss. Now let's interpret this very result. So let's assume, so you are having volume V, and in this volume, so S is a surface. So what is on the left hand side? Just interpret it. So this T00 is what? Energy density. This object is what? Now, what this represents? It will represent me the total energy, is it? So this object is what? Total energy. Okay. So now what it gives me? Rate of change of total energy in the volume V. Okay. So that means the energy in the given volume is changing. Okay. So what, when you observe at the surface, what will happen? So there will be actually the flux arising at the surface. Okay. Or you can see the flux through the surface. Okay. What kind of flux? It's actually the energy density flowing through what? Through that very surface per unit time. Clear? So it means this object should represent me what? The flux through the surface. So samajh clear? So what kind of flux it should represent me? Energy density. So samajh you know the quantity which represents the flux through the surface? Energy flux through the surface per unit area per unit time. What is that? Pointing vector. Okay. So that means this C times Pi0. So this should represent what? Components of pointing vector. So much more, because this will represent simply the flux. Okay? Clear? Flux through the surface S. So much more. So if you remember, okay, yesterday we have also done this thing. I told you this Pi is equal to ith component of this P, is it? Okay, let me write P mu first. 1 by C T mu 0 dV, is it? So if I take now P0, that is T00 is energy density. Now let's take ith component. It's 1 by C. So let's write volume V. So what I get? Ti0 dV. Clear? So much is it true? So what this will represent to me? Ti0. So it actually, this very integral gives me the momentum, is it? Three components of the momentum. A simple three vector. Okay, simple momentum of the particle. Clear? So if I multiply now this C times this very object, this represents me what? Pointing vector. So pointing vector in terms, in other words, it is simply the momentum transfer across the surface. Okay? So it is simply the momentum that is carried by, the electromagnetic field across this very surface. Okay? So this we have seen yesterday, it is actually the momentum, is it? Free momentum of the particle, and this Ti0 is what then? It should represent me the momentum density with, obviously, with 1 by C. Clear? So was there 1 by C here?
Yes,
No.
1 by C.
We have put 1 by C, okay? Now you got it, huh? So that is this Ti0 either represents the momentum density, okay? Three components of the momentum density are that is equivalent to the pointing vector, okay? So that means the momentum and the pointing vector has the same interpretation in terms of the electromagnetic field, okay? Okay, so now let's write the other terms. Let's write the other equation. Let's take nu is equal to, let's write J. Now let's write I. So that means I is equal to 1, 2, and 3. Special components. So what I am having? Partial mu, P mu, let's write I, that's equal to 0. So these are the other three equations. Clear? So let's write it. So it's partial 0, P0I plus partial J, because I have already used. Now let me write J this new, so that it becomes easier. G-I-I, because I comes before J. It is simple to tell it's I, J. Okay. So what this is, object is 1 by C, partial by partial T, P0J is equal to minus times partial I, Ti, J. Clear? So now let's integrate our volume. Volume V, so it is 1 by C. Okay, so I will write partial by partial T, integration over here, only T0J dV, that's equal to integration of volume partial I Tij dV. Okay, now this is again the divergence with respect to what? I component, is it? Forget about this J. So this is a divergence with respect to I. Apply Gauss law. So what you will get? Okay, so let me write here. So it's simply 1 by C partial E0 dV is equal to minus for surface. So it is some Tij. Okay? Clear? So now let's interpret it again. What this object represents me, the flux density, or it's actually the momentum, is it? 1 by C times this object is what? So this is the momentum of the particle, okay? So you are having now, the electromagnetic field carries the momentum. So let's take this very region. So in this region, what? So you are having momentum, it's changing, okay? So when you are having momentum changing, what will happen? So at surface you will figure out there is a flux. Flux of what? Flux of momentum, obviously. So what that represents me? Okay, anybody? So let's think this way. Okay, so if I apply, let's say you are having this very object, let's think this as a rubber. So you apply force per unit area on this very object. What will happen to this? It will deform, okay? It will deform in any direction. It will depend upon the way I am applying the force, is it? So in other words, the momentum, the rate at which I am changing the momentum here, what will happen? So the different deformations will arise, okay? Depending upon the direction of the momentum. Clear? So what these deformations will give me? It is actually the stress. Okay? So that means if you are having changing momentum in certain volume, so on the surface you will actually observe the stress. You got my point? Stress is actually what? It's force. Okay? So when you are changing the momentum, you will see there is a force acting on the surface. Okay? So it means the electromagnetic field, you change the momentum of the field here, so that will be, okay, you can see on this wall, on this very surface, as the force acting. Okay, so there is a force acting on this wall, and that force we call what? As a stress. Clear? That is why you are having the radiation pressure. If you are having, okay, so if you shine something with the light, so it exerts actually some kind of force on that very object. Although we are not able to observe in our daily lives how light, okay, let's say you are having some, think of the laser beam, okay, so what happens? Huh? So it exerts force on the, let's say, on the surface of my skin, okay, on the atoms of the skin. So I am not observing it in day-to-day life, okay, but it's actually there, although it's very weak. But if you are having strong fields, so you can observe it, okay. So then I can interpret this very object as what? Stress. So this will represent me the stress due to the field, okay. So it is due to general field. So now you are having, okay, for any kind of field, so what you have observed, you are having changing energy density. So it appears what? As a flux through the given surface. Now if this field exerts momentum, there is a change in momentum due to this very field, so it appears as what? It actually generates stress on a given surface. Okay? Clear? So therefore we can interpret these results, okay, the components of this very matrix, okay, this T mu nu, okay. So let's write it in the fashion of what? In its components. It's a matrix, is it? So what is, okay, let's call this as T00. Then what you are having? T01, T02, T03, okay, T10, T20, T30. Then you are having what? T11, T12, T13, T21, T22, 3, 3. Okay. So now look at this very thing. So this T00 gives me the energy density, is it? So this will simply represent me the energy density of the field. Okay, let's write it here. So let's call that energy density as this NCW. Okay. Then you are having this T01, T02, T0I components actually represent me what? The momentum, is it? But momentum is related to the pointing vector. Clear? So that means T01 will give me the X component of the pointing vector, T02 will give me the Y component, and so on. So I will write it like this in Sx by C. Okay? So, and Sy by C, Sz by C. Okay? So these will also represent the same thing. So you are having Sx by C, Sy by C, Sz by C. Now what remains there? The terms which contains all the special indices, okay? 1, 1, 1, 2. And I have told you what this T gives me? Just the stress, okay? So I will write that in terms of sigma. Let's write sigma xx, sigma xy, sigma xz, okay? Sigma yx, sigma yy, and sigma yz, okay? Sigma zx, sigma zy, and sigma zz. Okay, so this object, these sigmas, okay, sigma ij, I write as simply Tij, so it gives me what we call it stress tensor. Okay, we call it as simply stress tensor. Okay, on this sigma ij, it how many components it has? Only 3 components. Sorry, 9 components. Okay, I goes from 1 to 3, j goes from 1 to 3. We call sometimes it as 3 stress tensor. Okay, because it's only having the special indices. Clear? So sometimes it is also known as, okay, we'll see in a moment. This sigma ij gives us the Maxwell's 3 tensor. Okay, Maxwell's stress tensor. We'll see, because we are doing it in the general case. Now we'll take the example of electromagnetic field. Clear? Clear? Any question? So now let's take the example of electromagnetic field, and then we'll do one subtlety is there in this stress, and we'll remove that. Okay. So what is our electromagnetic field? First, tell me what is this T mu nu. So let's take the example of EM field. So this object partial L by partial mu E mu. Okay. Sorry. So what is here? It is phi. Correct? And then partial mu phi minus G mu nu L. Where phi is a field. Is that true? Okay. So what is our field here? Anybody? So for EM field, our phi is what? Phi is simply, let's write as A alpha. Okay? So it's simply A. What I need to figure out? This very object. Is that true? I need to figure out this very object. So is there any error? Okay. So no, let's write T mu nu. So it's equal to partial L by partial mu A alpha. That's right. Then partial mu A alpha. Okay. The thing what arises here, you are having the same. So I am putting A alpha. It's a contracted index minus G mu nu L. Mu nu are free indices. Okay, what's our L? So let's take free field, only free field. So that means no interactions at all. So it's minus 1 by 16 pi c f mu nu f mu. Clear? So what I need to figure out? Partial L by partial. Okay? So can you do it? So you are having this mu nu here. You put some different indices, okay, to avoid any confusion, because I have already utilized mu and nu. So let's try alpha, beta, beta, gamma. Clear? So can you derive partial L? Partial L by partial mu A alpha. Can you do it? What it is? Anybody? So I will leave it as an exercise. It's a simple exercise here. Eh? So what is that? It's minus 1 by 4 pi. Okay? Minus 1 by 4 pi. Okay, then what you are having? Where should I write? Okay. So it's a partial thing. So now let's write it. So therefore this T mu nu. So it's very simple. You just differentiate. Yesterday I have done it. I have done it in the detail. So this kind of. So it's partial. So what you are having? So it's minus 1 by 4 pi something f mu alpha. Okay. Then partial mu alpha minus g mu nu. Okay, what's our L? So L is this thing. So C I have forgot. So there is a C as well. So there is a C g mu nu. So it's minus 1 by 16 pi c f beta gamma. So this is an. So it's minus 1 by 4 pi c f mu alpha partial mu alpha. Sorry, partial mu A alpha. Now let's go. Okay, plus 1 by 16 pi c g mu nu f beta gamma. Okay, so this is your energy momentum tensor. Everybody followed it? What I have done? Okay, so what I have calculated? I need to calculate this very objective. Okay, because this contains Lagrangian, is it? Okay, now look here. I have calculated this objective from this very Lagrangian. This is a free space Lagrangian. Okay, it turns out to be this Lagrangian is equal to minus f. Okay, so this derivative is equal to minus 1 by 4 pi c f mu alpha. Okay, clear? So I have substituted here and I have written what is the value of this L. Okay, so now you have to just be careful. You are having free indices mu and nu, is it? Mu nu arises. Okay, so you are having mu here, mu nu here. Okay, so you have to keep them intact. And other dummy indices you can put anything. Just like I have put beta gamma here, you put A, B, C, D, whatsoever. Okay, it's your wish. Okay, now look at this way. So this is our energy momentum tensor of what? Electromagnetic field, but it looks very ugly. Okay, so look here. So if I interchange, okay, I can see that T mu nu is not equal to T nu mu. So that means this very form. Okay, if I interchange mu and nu, let's interchange. I will write mu here, is it? Okay, so this very object is symmetric, but this object is not symmetric. So that means energy momentum tensor, what I have derived is not a symmetric energy momentum tensor. But I have started from here. If you see, this is the problem with this very energy momentum tensor. If you, okay, look at this very thing. If I interchange mu and nu in this very thing, let's interchange. So nu will be here, mu will be here. This is symmetric, okay? So this is not symmetric part. But I require my energy momentum tensor to be symmetric, okay? There are two reasons for it. Mainly two reasons why we require energy momentum tensor to be symmetric. First thing is angular momentum should be, if angular momentum is conserved, it requires energy momentum tensor to be symmetric. Second thing, in general theory of relativity, because we say the gravitation is due to what? The curvature of the space and time, it is actually source for itself. So the mass and space, okay, mass is the source of curvature of space and time, and that curvature larger curvature means the massive mass, is it? So this energy tensor is related to the energy density. Okay? So it is related to the curvature of space-time. There is an equation, Einstein's equation, like this thing. So I will tell you. So you are having on one side, you are having this energy momentum tensor, and another side you are having this very curvature, like this thing. Let me write. Sorry. Okay, mu. Let me mu down. Okay. So some constants here. So this is actually the curvature on this very side. Okay, and this is the what source? That's energy momentum tensor. Clear? So because it is the source for the curvature, and it requires, this equation requires T should be symmetric. Clear? So these are the mainly two reasons why we require this energy momentum tensor to be symmetric. Clear? Okay. So okay, next another problem why we need to symmetrize it. This object is non-unique. Okay? So this object is non-unique. Let's look at it. Then we can fix that very Lagrangian. Okay. So let me write it. So we require this T mu nu to be symmetric because general relativity, particularly Einstein's equation leads to symmetric T mu nu. Second thing, okay, conservation of angular momentum. We'll see this we'll see particularly, not this thing. Conservation of angular momentum, because if this point is out, it's not in our scope in this course. Conservation of angular momentum. Okay, and third point, that's a weaker point, non-uniqueness. Uniqueness of G. That's why we need to symmetrize, okay, this G mu nu. I mean to say we need to put it in the symmetric form. Clear? Okay, so let me do it. So remember this equation, please. So we should write it in some corner because I require it later on. Okay. So let's take this very thing, non-uniqueness. So we are having this very object of partial mu P mu nu is equal to 0. Okay, we will taking the third point. What I mean by this non-uniqueness. So it means I can add to this T some quantity such that the derivative is again 0. Okay. So let's say if you are having a differentiation of a function and you add function a constant, differentiation such as the same derivative of the function. Okay. Clear? The same thing arises here. So if I change the, okay, let me add. Okay. Let's add a term of the form, okay, like this thing, some partial alpha, some f mu nu alpha. Okay. So let me check whether this is the quantity. Okay. So this is antisymmetric. So this is the derivative with respect to alpha, and f. So this very quantity, f nu alpha, is an antisymmetric quantity in the last two indices. Okay, so it's f mu like this. Okay, so this is an antisymmetric quantity, this f, in which indices? last two indices. So that means I am adding an a derivative of an antisymmetric quantity to this very object. Clear? To which object is this T mu nu? Okay. Let's add a term of the form this to T mu nu. That is like this thing. So I am changing this T mu nu to partial alpha F mu nu alpha. Clear? Now let's check whether this object satisfies me this equation or not. Okay? So let's check. So I can write it partial mu T mu nu plus partial alpha F mu nu alpha. Okay? So that's equal to, so T mu, okay, partial mu T mu nu plus partial mu partial alpha F mu nu alpha. Okay? So sorry. So let me write it as an antisymmetric in alpha and mu. Let's write it this antisymmetric in alpha and mu. Alpha mu. Like this. So I will choose it an antisymmetric at least in two indices. You can choose it as an antisymmetric in all the pairs, interchange of any pair, but I will choose it at least antisymmetric in what? Mu and alpha. The reason being here, so I am having a symmetric part here, okay? This is symmetric in mu and alpha, okay? So if this is antisymmetric in mu and alpha, what this will yield me? Tell me. So it's a symmetric multiplied by antisymmetric, okay? So this, okay. So this is symmetric and this is antisymmetric. What this yields me? So that means this product is equal to 0. So what this object is? By definition it is equal to 0, is it? So that's equal to 0. What it means? So the derivative of this object is what? So let's call this as, suppose T tilde mu nu symmetric. Okay? So that means partial mu T tilde mu nu, that's equal to 0. Okay, so that means it satisfies the same equation. Clear? So what we need to fix then? We need to fix this arbitrariness in energy momentum tensor. Clear? So it means, okay, look here, what I have done. Okay, let me put it in the simple terms. I have taken this energy momentum tensor, okay, this very object, and I have added, okay, I have added some quantity here, and I have shown the derivative of this very entire object is equal to 0. So it means this object is non-unique. Is that true? Non-unique is up to this very term. So this result shows me this T is simply non-unique. Okay, that means I can add certain terms to this T mu nu such that this non-uniqueness is removed. Clear? समझ आया? You got my point? Okay. Now let's okay. So that's why we can add. So if I am having a non-unique T mu nu, I can add any term to this thing such that the differentiation of that very term goes to 0. Clear? So I can form any kind a term kind of this thing. Okay? So this F is any arbitrary object. There is no problem with this. F can be any damn thing. Okay? So only the thing is that you need to adjust indices in this very fashion. Okay? समझ आया? Clear? समझ आया? So what I have chosen? I have chosen only this mu and nu to be antisymmetric. You can choose all the three indices, okay, any pair of interchange of indices as an antisymmetric. Okay? Clear? Okay. So this very term, so it means I can add any term to this T mu nu such that the differentiation of the total term becomes 0. Okay? So this is the way we can remove the arbitrariness. I will show in a moment when we will do the electromagnetic tensor. Okay? I mean the energy momentum tensor for the electromagnetic field. Here we can add an arbitrary term such that we can make this T mu nu to be unique. Clear? Okay. Now let's go to this the conservation of the angular momentum. Okay, now tell me how we define the angular momentum in simple terms. So you are having Lx. Okay, let's write angular momentum. Wait, any problem? Better? Huh? X, Py, sorry, Lz, let's write Lz, X Py minus Y, teacher, Px. Is this? So is this how you write the angular momentum? Now if I am having, now since we are in the four-dimensional space-time, okay, so there can be the rotation in which, okay, so and so on. So you can be having rotation in xt plane, yt plane, zt plane, is it? And xy plane, yz plane, and zx plane. All these things planes are involved, okay? So that means, let's say if I am having rotation in xt plane, let's call that rotation. Okay, let's write what I will be having. How I can write? Yes? Just tell me. So simple. Okay, let's write. So you will be having, let's say, xt plane, or let's take zt plane. Zt plane means what? Okay. So we can form this kind of combination. Okay, just look. We can form like this: T, let's assume Px, okay, minus x momentum along t direction, okay, pt kind. Let's put these this kind of variables, okay. So what you need, x and p. So I am saying t, px, and although this does make okay. Does this make sense? Huh? Does this make sense? So you can write, let's say, CT here and CT here. CT is the length, okay? So it's the other length. Okay, so that means this is the length multiplied by the momentum, and length multiplied with momentum, but this momentum is along the CT direction, okay? Got it? So it is the component of the momentum along CT. What is that? That's actually the energy. Okay, sir? Momentum, component of the momentum along this t direction is what? E by c, is it? Energy. Okay. So that means I can form all these possible combinations. Clear? Now if I write in this fashion, now let's generalize this definition, I mean to put all these components in the four-dimensional form. So can I write like this thing? X mu, P mu minus, okay, X mu, P mu. Okay, let me write both upper indices. Can I write it? So both are, let's put mu is equal to 0, or let's say mu is equal to 1, nu is equal to 2. Okay, let's write this way. Let's figure out something. Mu is equal to 1, nu is equal to 2. What you will get? So x1, that's x. What is p2? That's py, is it? Minus, what is x2? So that's y. And what is p1? That is px. What you got? Z component of the angular momentum, is it? So this is simply the generalization of this formula of what? Angular momentum in 4 dimensions. Clear? Now if I can put it in this fashion, okay, if dp is the infinite, okay, small momentum, okay, 4 momentum, then I can write this angular momentum to be, okay, so we define this as a tensor. Okay, so how many components you are having? 2 components, mu and nu, both are free indices. Clear? So we define this angular momentum as, if dp is the small momentum, like this thing, x mu dp nu minus x nu dp. So this is how we define what? 4 momentum. Clear? You got it? Huh? So in other words, the object in these braces, it should represent actually the angular momentum density. And I am integrating that, and getting angular momentum back. So I have written it as in terms of m. Okay. So now let's write this dp in terms of this tensor, t mu nu. What is this P? Okay, P mu is equal to 1 by C integral of P mu 0, or let's say mu lambda dx lambda. Okay, so this is how we define it. In general, we define it in this way. Okay, so I can write that it as 1 by C integral x mu. Okay, what is dp nu? So it is t nu lambda. Okay, then minus x nu. So it will be t mu lambda. Okay. Clear? So now how many indices are here? I need to tell you something why I have to put it in this fashion. Okay, so forget about this ds lambda, forget this object. So how many indices this have? 3 indices, is it? So it means it's a rank 3 tensor object in the braces. Okay, so you are having a rank 2 tensor. Okay, rank 2 tensor is related to what? A rank 3 tensor. Now look here, you are having a rank 2 tensor here. It is related to a rank 1 tensor. I started with J mu, simple J mu, if you remember it. J mu ds mu. And it is related to what? Q. So that's a rank 0 tensor. So this is neither charge, this is neither current, this also what? Okay, if it is conserved, this is also what? A neither, neither current. We simply call it as a neither current, okay? Now what does it mean? So if you are having P mu in this fashion, that means derivative of this object has to be equal to 0, okay? So if P mu is conserved, derivative of this object is 0. If Q is conserved, derivative of this term is what? 0. If let's say M is conserved, derivative of this object is 0. So let's call this object as this M mu lambda, okay? Okay, so that means conservation of angular momentum M mu implies actually. So let me write. So which index is contracted? Tell me. In this very object, which index is contracted? Lambda. Now if you are having this lambda is contracted, that means I need to put a differentiation with respect to tan lambda, okay? So mu is contracted, I need to put differentiation with respect to this mu, okay? So it means I need to put differentiation with respect to lambda, like this thing. M mu lambda, okay? So it implies this very object is 0. So I have assumed conservation of angular momentum, conservation implies this very equation, clear? So now let's look what it yields me. So what is this M? So it's equal to x mu t nu lambda minus x nu t mu lambda. Okay, that's equal to 0. Clear? Okay. So let's differentiate it. So it's partial lambda x mu. Okay. So let's differentiate by parts. Then you are having t nu lambda plus x mu separate partial lambda t nu lambda. Okay. Then minus differentiation of this thing partial lambda x nu t nu lambda. Then you are having this minus, okay, x nu separate partial lambda t nu lambda, that's equal to 0. Okay. So just differentiation by parts. Now by definition, partial lambda t nu lambda is what? This is 0. Is that true? Because we are assuming what? Partial mu p mu nu is equal to 0. Is it? So similarly, this very object is equal to 0. What remains? These two terms. Everybody has written it? Everybody is following what I am doing? No? Am I going fast? Okay. Okay, so what remains there? Can anyone tell me what this object is? It's like this thing. Partial by partial x lambda, x mu, okay, then you are having t nu lambda, minus partial by partial x lambda, x nu, t nu lambda, that's equal to 0. Can you tell me? So this is simply delta mu delta mu lambda T mu lambda minus delta nu lambda T mu lambda is equal to 0. It's simply delta function. Okay, so mu lambda will be replaced by mu, so it is T nu mu minus nu will be replaced by lambda will be replaced by nu is equal to 0. What it gives me? T mu nu is equal to T. So what it yields me? Symmetry. Okay, so that means conservation of angular momentum yields you what? A symmetric energy momentum tensor. Clear? So now let's go back to our example electromagnetic field. We are done. Just we are done, and then we will calculate its components in a step-by-step fashion. Okay? We are done. Just we are done. It's equal to minus 1 by 4 pi. Okay. F alpha partial A alpha plus 1 by, I have put C equal to 1, although there should be a C, I should put C explicitly. So it's okay. So this I had put earlier beta gamma because these are dummy variables and these are actually the additive terms. That's why I have put now alpha beta. Clear? So now is this symmetric? So this tensor, okay, we need to symmetric. It is not a symmetric one. Okay? We need, okay, since we have already told if this T mu nu is non-unique, is it? We can fix this symmetrization problem by adding a term, okay? And a term such that, okay, so it will symmetrize it, okay? Add a term to symmetrize it. Okay, so this is a term what I will add, okay? 1 by 4 pi C partial alpha A nu F alpha. Okay, so this is the term. I'll be adding this term to this very term. Okay, I mean this T mu nu. This will actually anti-symmetrize. Now look here. I have chosen. Okay, so this is a term. So you can consider. Okay, D alpha. I have chosen what? That partial alpha, some F alpha mu nu something whatsoever. Okay, and I have chosen that F to be antisymmetric in two indices at least. Now look here, you can say this A and F, it forms what? It is just like that three rank free tensor F alpha mu nu, is it? So if this is a kind of function A and F, it's a rank free tensor. Forget about this partial alpha. Okay, so others form actually a rank free tensor, is it? So much even? Okay, now if you see this F is the electromagnetic tensor, field tensor, it's antisymmetric in alpha and nu. So that means the condition is satisfied. I have chosen this F to be antisymmetric in any pair, so I have this as a pair. Okay, so that means I can add this very term to this very tensor. Clear? Samajh aao? So after adding this, so it implies therefore, so which implies, now let me write this very term. Okay, let's call this term as first. Okay, so I mean this first term, that's right. So it's minus 1 by 4 pi C F mu alpha partial mu A alpha, okay, plus therefore we get, so addition of these two terms is equal to partial alpha A nu F alpha mu. Okay, so now let's take F alpha mu. Okay, so this is F mu alpha, this is alpha mu. You can interchange the indices. So like this thing. So I can put minus 1 by 4 pi C F mu alpha partial nu A alpha, so minus 1 by 4 pi C, so it's C here, I always forget, partial alpha A nu, okay, then F mu alpha, correct? So you can take this F mu alpha common, so that's equal to minus 1 by 4 pi C F mu alpha. So what remains inside? Partial nu A alpha minus partial alpha A nu. Okay? So I can raise this, since alpha is a contracted index, I raise this alpha up and lower down this alpha. So it's like this thing, minus 1 by 4 pi C F mu alpha, okay, partial nu A alpha minus partial alpha A mu. Okay, can you tell me what this object is? So this is simply equal to F nu alpha. Okay, so what we have then, so this term I will write as minus 1 by 4 pi C F mu alpha F mu alpha. Okay, now look here, look at this very term. So this is already symmetric, this very part. Okay, so if I interchange mu and nu, this is already symmetric. Now if I interchange mu and nu, is this symmetric? So let's change this mu and nu. So put mu here, you put nu here. So is this, it is the same thing. You can then actually raise this up and lower down, okay, like this thing. Okay, so you can write this as F nu alpha F mu alpha. So that is same as F nu alpha F mu alpha. This is the same thing as this very term. Correct? So it means, so which implies therefore this T mu nu is same as T nu. So we have symmetrized this very tensor. Now let's take the trace of this T. Okay? So let's take this T mu mu. So if I take T mu mu, that is what? T00 plus T11 plus T22 plus T33. So let's put mu mu. So let's put nu as same as mu. Okay? Let's put. So that, so it's minus 1 by 4 pi C F mu alpha F mu alpha, like this thing, plus 1 by 16 pi C G mu mu, okay, F alpha beta F alpha beta. Can anybody tell me what this sum is equal to? Can anybody tell me the sum of these two terms? If you look carefully, what is G mu mu? It is sum of the diagonal terms of G, is it? So how much is that? What are the sum of the diagonal terms? Tell me. So, okay, expand it, you show it. It's equal to 0. Okay? So T mu mu is what? The trace of this energy momentum tensor is equal to 0. You should have been here instead of going up and down. Okay? So taller should go at the back. Take the simplest of the case. Let's take this T00. Let's write it. Okay? Let's write T00. So it's minus 1 by 4 pi C F0 alpha F0 alpha plus 1 by 16 pi C G00 F alpha beta F alpha beta. Let's write it. Anybody can anybody tell me what this F alpha beta is? Okay? Anybody? Twice B square minus E square. You remember it? This way. What is G00? It's 1. Now let's write it. So what this is? So look here. If I write alpha is equal to 0, okay, let me write. So it is F4 pi by C F00 F00 plus F0I F0I. There is a sum over I. Okay, plus 1 by 8 pi C E square. tell me what this F00 is? It is 0. So it's simply minus 1 by 4 pi. See, what is this F0I? What is F0I? It's, okay. So what this is? So this object is equal to 0. What F0I is? It's minus EI. Is it? I is the component of the electric field. What this object is? Okay, so this object is minus EI. What this object is? It is simply EI. So what is EI into EI? It's EI square. So it means it is simply vector E square, but there is a minus sign, so it's minus E square. Okay, then you are having plus. Is it true? So then you are having this B square minus E square divided by 8 pi C. Now tell me, so, okay. Now tell me what it gives me. It gives me simply E square plus B square divided by 8 pi C. What this object is? What is the energy density of the field? E square plus B square. Okay? So it is the energy density. There is actually the problem, the C has kept in somewhere. Either there should be no C or there should be C. So we have come across with this C. Just check it in your calculations. So where this C has come. So there it should be only E square plus B square by 8 pi. So there should be no C. Yes, there should be no C. We have come across C, factor of C somewhere. So you need to check it. Now let's take T0I. Let me take T0I. So I will take only T0I. These are simple calculations, you will learn it. Okay. So let's take T0I. So what it gives me? So I will not take C here. Let's not take C. There is the C. I don't know why it has come. So I will not take C. So it's minus 1 by 4 pi F0 alpha Fi alpha plus 1 by 16 pi. So it is G0I F alpha beta. Look how simple this calculation is. G0I is all the other off diagonal terms of G are 0, is it? So this is equal to 0. So this object is equal to 0. So now look here. So I can write minus 1 by 4 pi. So what is this F0? Okay. So I can write this simply F0. Okay. F0I. Sorry. F00, that's equal to 0. Okay. If you sum over, let's say alpha is equal to 0, 1, 2, 3. F00 is 0. That term I am not writing. So it is simply Fij. Okay. Sorry, I will write J. Anybody? What this object is? So what this object is? It is Ej. What this object is? Epsilon I J K B K. What is that equal to? So this is actually minus with a negative sign. Minus EI. Sorry. So this object is equal to minus and this object is plus. So it's equal to 1 by 4 pi. Okay, so now you are having again this problem. Okay, it's okay. So it is simply E cross B. So what this object is? What this object is? Anybody? So it's pointing vector, is it? C by 4 pi, it's a pointing vector, okay? Okay, similarly, now let's take Tij. Can you do yourself this Tij? So let me write this Tij. So that's equal to, so it is done on notes. So you can see it. So if I take Tij, it's equal to 1 by 4 pi minus Ei Bj minus Bi Bj plus half of delta Ij E square plus B square. Okay, so that's equal to actually. So you are having this Maxwell stress tensor. It is actually Maxwell stress tensor. So sigma Ij is equal to 1 by 4 pi, okay, minus Ei Ej minus Bi Bj, okay, then you are having plus delta Ij, okay, so let me put it down here, delta density. So this is the Maxwell's plus density. Okay, so this is all about the tensors. So this finishes.